Have you ever wondered what the deepest silence in the world sounds like? Not the quiet of a forest at night or the hush of a snowfall, but a true, profound, crushing silence. The kind of silence that exists under the weight of an entire ocean, in a place so far from our world it feels like another planet. A place where sound itself doesn't behave like it should. Welcome, everyone. If you're fascinated by the unseen, the unexplored, and the utterly extreme corners of our planet, you are in the right place. Before we descend into the abyss, make sure you've hit that subscribe button and rung the notification bell. This journey will change how you hear the world, both above and below the waves. And when we're done, I'd love to know, where in the world are you watching from and what time is it for you? Drop a comment down below. Let's connect across the oceans and time zones. Today, we are exploring the final frontier on Earth, the Mariana Trench. We're not just going to talk about how deep and dark it is. We're going to explore its most mysterious property, its sound, or rather, its profound defiance of it. How does the most isolated realm in our oceans warp, absorb, or even silence the very waves that let us communicate? This is the story of pressure that could crush a tank, cold that numbs the soul, and a quiet so deep it has its own secrets. Strap in. We're going down. Let's start by getting our bearings. Picture the vast expanse of the western Pacific Ocean east of the Philippines. About 200 kilometers or 124 miles east of a chain of islands known as the Marianas, the seafloor does something extraordinary. It doesn't just dip, it plunges. It cracks open into a crescent-shaped scar on the Earth's crust. This is the Mariana Trench. Its numbers are staggering. It stretches for over 2,550 kilometers. That's about 1,580 miles. At its widest, it's about 69 kilometers or 43 miles across. But those numbers are what defines it. It's the vertical drop. Imagine taking Mount Everest, the tallest mountain on land, and submerging it in the ocean at this spot. Unbelievably, its summit would still be over a mile, about 1.6 kilometers, beneath the surface of the water. We are talking about a depth so profound it redefines our sense of scale. The deepest point in this trench, and therefore the deepest known point in all the world's oceans, is a small slot-shaped valley called the Challenger Deep. Its maximum known depth is around 10,984 meters, or just over 6.8 miles straight down. To put that into perspective, a commercial airliner cruises at about 10,000 meters. We are talking about a depth equivalent to flying a plane upside down into the abyss. Now let's talk about what this depth means. For every 10 meters you descend into the ocean, the pressure increases by 1 atmosphere. That's another 14.7 pounds pressing on every square inch of you. Do the math. At the bottom of the Challenger Deep, the water column above exerts a pressure of about 1,086 bar. That's over 1,000 times the atmospheric pressure we feel at sea level. More graphically, it's like having 8 tons, the weight of a large truck, pressing down on every square inch of surface. This isn't just pressure. It's a force that fundamentally changes the properties of everything it touches, including the very way sound travels. And it's cold. The temperature at the bottom hovers between 1 to 4 degrees Celsius, 34 to 39 degrees Fahrenheit. Combined with the eternal darkness and unimaginable pressure, this creates an environment that, for most of human history, we believed was completely sterile, a liquid desert. We were so wrong, but we'll get to the life that thrives there soon. First, we need to understand why this trench exists at all. To truly grasp why this unfathomable gash in the ocean floor exists at all, we have to pull back the curtain on one of the most powerful and fundamental forces shaping our planet. Forget random cracks or ancient wounds. This is an active, dynamic, and breathtakingly slow-motion crash scene, happening right now, 7 miles beneath the waves. It's the story of two gigantic pieces of Earth's shell going head-to-head in a battle of density and destiny. And it all revolves around a single, magnificent word: subduction. So let's break down this grand geological drama in the friendliest way possible. Imagine the Earth isn't a solid, static ball, but more like a slightly runny, hard-boiled egg that's been left out too long. The shell has cracked into a puzzle of giant pieces. These pieces are our tectonic plates. They're not just the continents you see on a map. They include the vast, hidden floors of the oceans too. These plates are constantly, imperceptibly on the move, floating on a hotter, softer layer of the Earth's mantle beneath them. Now picture the western Pacific Ocean. Here, two of these colossal plates are on a collision course. On one side we have the behemoth, the Pacific Plate. It's vast, covering much of the ocean floor beneath the Pacific Ocean. On the other side we have the smaller but no less important Mariana Plate. Their boundary isn't a neat, polite line. It's a chaotic, grinding, messy frontier where these two titans meet. And when they meet, one has to give way. This is the essence of a subduction zone, a place where one tectonic plate is forced to dive down beneath the edge of another. But why does one plate go down and the other ride over the top? It all comes down to a simple sink or float principle: density. Think of it like a grand geological game of which one is heavier. Oceanic plates, like our Pacific Plate here, are made of basalt rock. Over millions of years, as they move away from where they were born at mid-ocean ridges, they cool down. And as they cool, they become denser and heavier. The Pacific Plate in this neighborhood is a real elder statesman. It's some of the oldest ocean crust on our entire planet, up to a staggering 170 million years old. That's an immense amount of time to cool down and become incredibly dense and heavy. The Mariana Plate, on the other hand, is a different story. It's a smaller plate, and the crust in this region is generally younger and therefore less dense. So, when the old, cold, dense Pacific Plate meets the younger, more buoyant Mariana Plate, the outcome is inevitable. Like a piece of thick, stale crust of bread sinking into a pot of hot soup, the denser Pacific Plate surrenders to gravity. It begins to bend, crack, and inexorably plunge downward, thrust beneath the lighter Mariana Plate. That line where this dramatic descent begins, the exact point where the seafloor takes a nosedive into the abyss, that line is the Mariana Trench itself. It's the surface scar, the visible evidence of this incredible downward journey. Now let's visualize this plunge. The Pacific Plate doesn't just drop vertically like an elevator shaft. It bends. Imagine taking a stiff piece of plastic and slowly pushing one end under a rug. The plastic will curve downward. That's what's happening to the plate on a scale of hundreds of miles. As it bends, it creates that iconic, mind-bending V-shaped profile of the trench. The process is slow, moving at speeds measured in centimeters per year, about the same speed your fingernails grow, but the power is unimaginable. This bending isn't gentle. It creates immense stress, causing deep cracks and fractures in the rock. Seawater, under the immense pressure of the ocean, is forced down into these cracks, seeping deep into the fabric of the descending plate. And this is where the story gets even more interesting, and where we start to see the beautiful, poetic circle of destruction and creation. As the Pacific Plate continues its descent, it goes deeper and deeper into the Earth's mantle, which gets progressively hotter. The plate, which started cold at the surface, is now being heated from the outside in. But remember that seawater we mentioned, locked in the minerals of the rock. That becomes a critical agent of change. At a depth of about 60 to 100 miles beneath the surface, the combination of immense heat and pressure becomes too much for the water-bearing minerals in the sinking slab. They break down in a process called dehydration, releasing their stored water. But this isn't water as we know it. At these incredible temperatures and pressures, the water exists as a supercritical fluid, a hot, buoyant, mineral-rich substance that acts like a powerful chemical agent. This fluid rises upward from the sinking plate and infiltrates the hot mantle rock of the overlying Mariana Plate. Here's the magic trick. This released water dramatically lowers the melting point of the mantle rock above it. It's like spreading salt on an icy road. It makes the solid rock more likely to melt, even at temperatures where it would normally stay solid. This process, called flux melting, generates pockets of magma, molten rock. And since this molten rock is hotter and less dense than the surrounding solid mantle, it begins to rise. Like blobs of wax in a lava lamp, these buoyant masses of magma squeeze and ascend through the overlying plate, traveling upward for dozens of miles. Eventually, this magma finds its way to the surface, but it doesn't erupt directly in the trench. Oh no, the trench is a zone of pure destruction, of downgoing material. The creation happens off to the side. This rising magma breaks through the seafloor of the overriding Mariana Plate, which lies to the west of the trench. Over millions of years, countless eruptions have built up a curving chain of underwater volcanoes parallel to the trench. Some of these volcanoes have grown so tall they have broken the surface of the ocean. And what do we call this string of islands? The Mariana Islands. Guam, Rota, Tinian, Saipan. These beautiful tropical islands are the direct children of the trench's destructive process. So, the very same geological force that creates the deepest hell on Earth is also the architect that builds islands that reach for the sky. It's the planet's most dramatic example of recycling. Old ocean crust is destroyed in the trench, and its materials are cooked, melted, and reborn as new land. This brings us to the user's second brilliant point. Why is the Mariana Trench so astonishingly deep? The Challenger Deep isn't just the deepest part of the trench, it's the deepest point in all the world's oceans. What makes this spot the ultimate champion of depth? Two main factors work together. First, as we've established, the Pacific Plate here is incredibly old and therefore incredibly dense. Density is the engine of subduction. The denser the sinking slab, the more readily and steeply it wants to dive into the mantle. In many subduction zones, like those along South America, the sinking plate is younger and warmer, so it sinks at a shallower angle. But here, the old, cold Pacific Plate is like a weightlifter ready to plunge. Studies show the slab beneath the Mariana Trench descends at one of the steepest angles on Earth. A steeper dive means the trench at the surface can form a deeper, more pronounced V. Second, and this is a crucial bit of the puzzle, the Mariana Trench is located far, far away from any major continent. Why does that matter? Think about other deep trenches, like the one off the coast of Peru and Chile. That trench is also phenomenally deep, but it's constantly being fed a thick soup of mud, silt, sand, and gravel, sediment, washed off the mighty Andes Mountains by massive rivers. This sediment acts like a geological dumping ground, partially filling the trench and making its floor shallower and smoother. The Mariana Trench has no such messy neighbor. There's no giant continent nearby dumping truckloads of sediment into its depths. It sits in the open ocean, far from large land masses. This means it remains a relatively clean and stark cut. The sediment that does accumulate on its floor is mostly very fine-grained ooze that drifts slowly down from the ocean waters above over eons, or material from nearby volcanic arcs. It's not enough to fill the profound chasm created by the steeply diving plate. The trench is allowed to be its full, deep, dramatic self, a pristine and stark scar on the planet's skin. So to wrap this all together in a neat bow, the Mariana Trench is not a static hole. It is an active, living geological feature. It is the visible proof of a titanic, ongoing struggle between two plates, where the older, denser Pacific Plate is losing, dragged down into the mantle by its own weight. This process of subduction carves the trench, fuels the volcanoes that build the Mariana Islands, and creates a realm of such extreme pressure and isolation that it defies our imagination. It is a place where the very rules of our world seem rewritten, born from the simplest of principles. The cold, heavy rock sinks, and the planet remakes itself in the fiery depths below. Now, let's dive into one of the most thrilling chapters of this story, the human quest to actually find and touch the bottom of this unimaginable place. It's a tale of curiosity, courage, and some absolutely brilliant, harebrained engineering that spans over a century. It begins not with fancy submarines, but with a ship, a very long rope, and a whole lot of patience. Our story starts in the year 1875. Picture a grand, three-masted sailing ship called the HMS Challenger, plowing through the vast Pacific. This wasn't just any ship. It was on the world's first major scientific expedition dedicated entirely to understanding the ocean. Its mission was to discover what lay beneath the waves in an age when many still believed the deep sea was a dark, lifeless desert. As it tried to make its way to Guam, baffling winds blew it off course, west of its intended path. By pure, incredible luck, this accidental detour took it right over a part of the seafloor that would later become famous. So, how do you measure the depth of the ocean when you can't see the bottom? Their method was as simple as it was terrifying. They used a device called a Bailey sounder, which was essentially a long, weighted rope. But this was no ordinary fishing line. The weight itself was a massive 450-pound lead ball. Imagine the crew lowering this monstrous weight over the side of the ship, paying out miles and miles of heavy hemp rope, hand over hand, waiting for the moment the slack would finally go out of the line, a sign it had hit the solid seafloor far, far below. It was a slow, arduous, and dangerous process. The strain on the ship's rigging and the rope itself was immense, and they even used a system of rubber band accumulators to absorb the shock and prevent the line from snapping. On March 23, 1875, after what must have felt like an eternity of lowering, the rope went taut. They hauled it all back in and did the math. The measurement was staggering, 4,475 fathoms. In modern terms, that's about 8,184 meters, or over 5 miles straight down. The crew of the Challenger knew instantly they had found something extraordinary. They had discovered the deepest sounding anyone had ever recorded. They didn't have a name for the trench yet, and they certainly had no idea they were sitting right next to the absolute deepest point, but they had found the neighborhood. They had proven there were chasms in the earth that dwarfed our tallest mountains. The world was shocked. Fast forward 75 years. The world had changed dramatically and technology had leaped forward. In 1951, another British survey ship, named HMS Challenger II in honor of its predecessor, returned to the scene. Its mission was to revisit that mysterious deep spot and find out just how deep it really went. This time, they had a new tool, echo sounding. Instead of a physical rope, this technology used sound waves. The ship would send a ping of sound down through the water column. That sound wave would travel to the seafloor, bounce off, and travel back up to the ship. By meticulously timing how long that round trip took, and knowing the speed of sound in water, you could calculate the distance, the depth. But even this advanced tech had its limits. When they got readings over 10,000 meters, it was so deep it was almost beyond their echo sounder's ability to believe. So, just to be absolutely sure, they went old school again. They dropped a weight on a taut wire and measured a depth of 10,788 meters. Later, after boosting their echo sounder's power, they got an even more precise reading, 10,863 meters. This was the moment they realized the 1875 Challenger had only found the outskirts. The true abyss was even deeper. To honor both pioneering ships, they named this deepest point the Challenger Deep. The modern era of deep-sea exploration had officially begun, and with it came a tantalizing new question. We could measure it from the surface, but how on earth could we ever send something, or someone, down there to see it? How could you possibly communicate with a vessel under thousands of tons of pressure, in total darkness, 7 miles down? This brings us to our first true heroes of the deep, and one of the strangest, most wonderful machines ever built. Its name was the Trieste, and it was a bathyscaphe. Now, that's a fancy word, but you can think of it as a deep-sea balloon. Instead of being filled with hot air for going up, it was designed to go down. The main part you see in pictures is its huge float, which was filled with 50,000 gallons of gasoline. Why gasoline? Because it's lighter than water, giving buoyancy. And crucially, it doesn't compress much under pressure, so the tanks wouldn't be crushed. Hanging beneath this giant gasoline float was a perfectly spherical, heavy metal crew cabin, just big enough for 2 people. This sphere was the heart of the operation and a masterpiece of engineering. For the historic dive, the Trieste used a sphere forged by the famous German Krupp steelworks. Its walls were a whopping 127 millimeters, 5 inches, thick to withstand the crushing pressure. The only window was a single, cone-shaped plug of clear acrylic, because it was the only transparent material strong enough. Getting in and out was an ordeal. They had to climb down a vertical tube into the sphere and then seal a 350-pound hatch above their heads. Once inside, they were in a self-contained world with its own oxygen supply, carbon dioxide scrubbers, and batteries for power. On January 23, 1960, in rough seas with 25-foot swells, Swiss engineer Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed into that sphere. The conditions were so bad that a last-minute message arrived from headquarters ordering them to cancel the dive. But by the time it was received, the Trieste was already 20,000 feet down and committed. They sealed the hatch, and at 8:23 in the morning, they began their descent into the unknown. For nearly 5 hours, they sank into the darkness. It was a quiet, cold, and tense elevator ride. The temperature inside dropped to about 45 degrees Fahrenheit, 7 degrees C. At about 30,000 feet, a loud bang and a jolt shook the entire vessel. They later discovered a viewing port in the flooded entry tube above them had cracked. It was a heart-stopping moment, but the vital pressure sphere holding them was intact. They made the courageous decision to continue. Finally, their depth gauge read over 37,000 feet, and their sonar began to ping back a signal from the bottom. Piccard turned on the powerful quartz arc lights. Through the small, thick window, they saw something no human had ever seen before: the bottom of the Challenger deep. It was covered in a pale, diatomaceous ooze, a fine, silty mud. And then, in a moment that would change biology forever, Piccard reported seeing a living creature. He described it as a flatfish, like a sole or flounder, moving along the seabed. This sighting was monumental. It proved, against all odds, that complex life could not only survive but thrive under pressures that seemed designed to obliterate all matter. The scientific community would later debate that sighting. It might have been a sea cucumber, and we now think the absolute depth limit for fish is shallower. But the point was made. The abyss was teeming with life, not a barren wasteland. Their stay was brief, just 20 minutes. They couldn't take clear pictures because their landing stirred up a cloud of silt. They released ballast weights, iron pellets held by electromagnets, and began their 3-hour ascent back to the world of light and air. They had done it. Humanity had reached the deepest point. And then, for over 50 years, no one went back. The technological and financial challenge was simply too great. The Trieste was a one-of-a-kind marvel, but it was cumbersome, and its missions were limited. The deep ocean remained almost as mysterious as it had been before 1960. That is, until a famous filmmaker with a passion for exploration decided to take on the challenge. On March 26, 2012, James Cameron, the director of Titanic and Avatar, piloted his custom-built submersible, the Deep-Sea Challenger, to the bottom of the Challenger Deep. His craft was a sleek vertical torpedo, a stark contrast to the bulky Trieste. But the core challenge was the same: building a compartment strong enough to protect a human. Cameron's pilot sphere had steel walls 64 millimeters, 2.5 inches thick. Where the Trieste used gasoline for buoyancy, the Deep-Sea Challenger used a revolutionary material called syntactic foam. Engineer Ron Alum created this foam by embedding millions of tiny, hollow glass spheres into a special epoxy resin. This created a solid material that was incredibly strong, strong enough to have thrusters mounted directly in it, yet lighter than water, providing the buoyancy needed to return from the abyss. Cameron's descent was faster, taking about 2 hours and 37 minutes. His vessel was packed with modern technology: bright LED lights, 3D cameras, and robotic arms for sampling. He spent 3 hours on the bottom, exploring, filming, and collecting data, giving the world its first high-definition, color glimpse of this alien landscape. He saw not a flat, featureless plain, but a dramatic world of slopes and rocky outcrops. The journeys of the Trieste and the Deep-Sea Challenger bookend an incredible period of pioneering exploration. One was a brave, first-ever proof of concept, a triumph of pure guts and fundamental physics. The other was a high-tech solo mission that opened a new window for science and public imagination. They both answered the fundamental question posed by the Challenger expeditions. Yes, humans can go there. They proved that with enough ingenuity and courage, even the most extreme frontiers on our own planet are not beyond our reach. Since then, others have followed, like explorer Victor Vescovo, who set a new depth record in his submersible limiting factor in 2019. But these missions share a common, monumental challenge, one even more perplexing than pressure or cold: the challenge of communication. How do you talk to someone, or something, when it's 7 miles underwater? This is where our story turns from geology and exploration to physics. This is where we meet the true strangeness of the trench, its acoustic world. Sound is not like light down here. Light is quickly swallowed by water. After 1,000 meters, it's completely gone. But sound travels better in water than in air. It moves faster and farther. In the ocean, sound is the primary sense. Whales use it to communicate across entire ocean basins. Ships use sonar to see the bottom. But the Mariana Trench is the grand exception to the rule. Here, the normal rules of underwater sound are bent, broken, and rewritten. Now let's dive into one of the most mind-bending aspects of the Mariana Trench: how it completely rewrites the rules of sound. If you think about exploring the ocean, you might imagine bright lights cutting through the dark. But down here, light is practically useless. It gets absorbed by water in just a few hundred meters. The real light of the deep ocean, the thing that carries information across vast distances, isn't light at all. It's sound. And in the Challenger Deep, sound behaves in ways that would seem like pure magic anywhere else. Let's start with the biggest boss of the deep, the crushing pressure. We've talked about the numbers: over 1,000 times the pressure at the surface, the weight of a truck on every square inch. But what does that pressure actually do to the water itself? Imagine you're in a crowded elevator at the ground floor. People are standing with a little personal space. That's like water molecules at the ocean's surface. Now imagine that elevator goes down, and down, and down, and more people keep getting shoved in from above. By the time you reach the bottom floor, people are packed together, shoulder to shoulder, unable to move freely. That's what happens to water in the trench. The immense weight of the entire ocean column above literally squeezes the water molecules closer together. The water becomes denser. It's still a liquid, but it's a much tighter, more compact liquid. This increased density has a direct and profound effect on how sound travels. Sound, at its heart, is a pressure wave. It moves by making molecules bump into their neighbors. In air, molecules are far apart, so the sound wave has to push them over a distance to reach the next one, which makes it travel relatively slowly, about 343 meters per second. In denser water at the surface, molecules are already closer together, so the bump travels faster, about 1,500 meters per second. Now, in the hyperdense water at the bottom of the trench, the molecules are packed incredibly tight. When one molecule gets bumped, its neighbor is right there. This allows the sound wave to propagate even faster. So our first rule is, as pressure increases, the speed of sound increases. But wait, it's not that simple. There's another player in the game: temperature. We all know the trench is freezing, just a degree or two above 0°C. And temperature has the opposite effect on sound speed. In warmer water, molecules have more energy and vibrate more readily, making it easier for a sound wave to pass through. In colder water, molecules are sluggish and slow. Think of trying to pass a wave through a crowd of excited, jumping fans at a concert versus a crowd of sleepy, stationary people in a cold queue. The excited crowd transmits the wave much faster. So, colder water typically slows sound down. Now here's the fascinating tug-of-war that defines the ocean's acoustic personality. In the upper layers of the ocean, temperature is the dominant force. As you go down from the warm surface, the temperature drops rapidly, and so does the speed of sound. This creates a descending highway where sound speed gets slower and slower. But then, At a certain depth, usually around 1,000 meters, the temperature stabilizes, becoming uniformly cold. From this point on, the relentless increase in pressure takes over as the boss. The speed of sound stops decreasing and begins to increase again all the way to the bottom. This creates a fascinating structure within the ocean, a kind of acoustic valley or channel. The depth where the speed of sound is at its absolute minimum is the axis of this channel. It's called the SOFAR channel, the sound fixing and ranging channel. This channel is nature's most incredible long-distance telephone line. Why? Because sound waves are lazy. They always bend toward the region where sound speed is slower. Imagine you're driving a car and one side of the road is thick mud slow, and the other is clean asphalt fast. Your car would constantly pull toward the muddy side. Sound waves do the same. When a sound is generated near the SOFAR channel axis, its waves get trapped. They can't escape upward because the warmer water above is faster, bending them down. They can't escape downward because the high-pressure water below is also faster, bending them back up. So they bounce along this channel, zigzagging for thousands of miles with barely any loss of energy. A whale's song or even a small explosion in the SOFAR channel can be heard across an entire ocean basin. But the Challenger Deep doesn't play by these rules. It exists in a place called the Deep Sound Channel. Remember, the SOFAR channel has a minimum speed at its axis. The Deep Sound Channel is the region below that, where pressure has fully taken command and the speed of sound is now steadily increasing all the way to the seabed. The trench is not in the trapping zone, it's in the basement below it. This creates a bizarre and unique acoustic environment. Think of the SOFAR channel as a busy, resonant subway tunnel running through the middle of the ocean. The Challenger Deep is a silent, dead-end service tunnel far beneath the subway line. Sounds from the busy world above, whale songs, distant ship propellers, even earthquakes, can have their downward curving paths bent into the trench. It's like noise from the street filtering down into a deep basement window. However, a sound generated in the trench itself has a much harder time. If it tries to go up, it hits the high-speed wall of the pressure-dominated water, which bends it back down toward the seafloor. It's partially trapped. The trench, therefore, acts as a kind of resonant cave. Some frequencies of sound might echo around, while others are swallowed. It's an acoustic isolation chamber, but one that still listens to the distant rumblings of the planet. To map this invisible highway system, scientists use a crucial instrument, the CTD. This stands for conductivity, temperature, and depth. It's a cluster of sensors typically mounted on a large metal frame called a rosette, which is lowered from a ship on a cable. Here's what each sensor tells us. Conductivity tells us how well the water conducts electricity, which directly relates to its salinity, saltiness. Saltier water is denser and affects sound speed. Temperature is measured with highly precise thermometers. Depth is calculated from the immense pressure measured by strain gauges. By lowering a CTD through the water column and taking millions of measurements, scientists can build a perfect profile of the water's properties at every meter. Plug this data into equations and voila, you have the sound speed profile, a detailed roadmap that shows exactly how fast a sound wave will travel at any given depth. For anyone trying to communicate with a submersible or listen to the trench, this profile is their essential GPS. It tells them where sound will bend, where it might get trapped, and how much energy it will lose. Now, how do we actually listen to this silent, pressurized realm? We can't just dangle a microphone on a string. The pressure would crush a normal device into a tiny ball of junk. This is where engineering brilliance meets deep-sea curiosity. One of the coolest tools built for this job is called deep sound. Deep sound isn't a ship or a fixed buoy. It's an autonomous, free-falling acoustic platform. Imagine a sophisticated deep-sea elevator designed for one job, to carry a microphone to the abyss and back. It was developed by the genius minds at the Scripps Institution of Oceanography. The heart of deep sound is a hydrophone, an underwater microphone designed to withstand insane pressures. But this hydrophone isn't just slapped into a metal box. Its delicate electronic brain is housed inside a sphere made of Vitrovex glass. Why glass? It might sound fragile, but this isn't your kitchen window pane. Vitrovex is a special type of borosilicate glass that is incredibly strong under uniform, crushing pressure. Think of the classic high school science experiment where you try to crush a glass-graduated cylinder with your hands. It's nearly impossible because the force is evenly distributed. A sphere is the perfect shape for this, handling pressure from all directions equally. This glass sphere protects the precious recording hardware. The mission of deep sound is elegant in its simplicity. Scientists drop it overboard. It's weighted, so it silently free falls for hours, sinking deeper and deeper into the darkness. As it falls, its hydrophone is listening. Once it reaches a pre-programmed depth or touches the seafloor, a clever release mechanism is triggered. Maybe it burns through a small link with an electrical charge, or it releases a magnetic latch. The weights drop away, and the now buoyant glass sphere with its hydrophone safely inside begins a long, slow float back to the surface. Once it pops up, it transmits a location signal to be retrieved, its hard drive full of the secrets of the deep. In 2009, Deep Sound undertook a historic mission to the Mariana Trench. It recorded ambient noise from a staggering depth of over 8,400 meters, not quite the very bottom, but deep into the Hadal Zone. So, what did it hear in this alien acoustic landscape? The recordings revealed something surprising, not cacophony, but a surprisingly smooth, low-frequency rumble. Let's unpack that soundscape. That constant rumble is the voice of the Earth itself. It's the sound of distant earthquakes, seismic waves traveling through the crust and coupling into the water. It's the groans and moans of baleen whales, like blue or fin whales, from the world miles above, their super low frequency calls being one of the few things that can travel down into and resonate within the trench's deep sound channel. It's also the sound of distant storms on the surface, their energy transferred into underwater waves. And underpinning it all is the constant, gentle noise of water moving over the seafloor, and perhaps even the tectonic processes of the subducting plate. It's not silence. It's the deep, slow, ancient heartbeat of the planet, heard from its deepest chamber. This is the profound paradox of the Mariana Trench's sound. It is a place of extreme isolation, a place where local sound is trapped, yet it is also a place that listens to the global orchestra of Earth's motions. It defies simple rules, creating an acoustic environment that is as unique and extreme as its crushing pressure and eternal darkness. Understanding this isn't just academic. It's the key to unlocking communication in the deep, to listening for life, and to hearing our planet's deepest, most hidden pulse. But listening is one thing, talking is another. For James Cameron's 2012 dive, communication was a life-or-death engineering challenge. His team turned to an Australian company, L3 Oceania, with just 6 months to spare. They needed a system that could send both voice and crucial data, oxygen levels, battery status, depth, between the submersible and the support ships on the surface. The problems were immense. First, the sheer distance. Sound waves weaken over range. Second, the noise of the ocean itself. Waves, sea life, and most problematically, the noise from the support ship's own engines and propellers. Third, the weird acoustic properties of the trench water could bend and distort signals. The solution was a masterpiece of adaptation. They used a system called the UT-3000 underwater telephone. For voice, it used standard analog underwater telephone technology. For text and data, it used a sophisticated digital system called MASQ, Multiple Access Spread Spectrum, which is designed to be highly resistant to noise and distortion. The modem was mounted outside the sub's pressure sphere to save space, connected to Cameron inside via a simple headset and a tablet for text. But they hit a snag. The noise from the main support ship, the Mermaid Sapphire, was too loud to hear the faint signals coming from the deep. Their solution was brilliantly low-tech. They used a secondary, smaller boat, a rigid-hull inflatable that could drift with its engines off, listening in perfect quiet. They also lowered the hydrophone on the main ship 100 meters down on a long cable to get it away from the noisy surface water. In the end, communication worked like a relay. Commands went down from the quieted main ship, and Cameron's voice and data came up to the silent small boat, which then radioed them back to the main ship. And it worked. At 7:52 a.m. on March 26, Cameron touched down. One of the first voice messages to reach him was from his wife, Susie, on the surface ship. He was able to reply, solidifying a human connection across an almost interstellar distance. He later said, "It was amazing to talk to my wife Susie from the deepest point in the world's oceans." This dance with sound in the trench has even been used to measure the trench itself with incredible precision. In a 2014 expedition, scientists deployed two deep sound platforms. One, tragically, imploded under the pressure at about 9,000 meters, but that catastrophic event became a scientific gift. The other instrument recorded the powerful shock wave of the implosion. This shock wave echoed between the seafloor and the sea surface multiple times. By meticulously timing the echoes and knowing the precise sound speed profile of the water column, the scientists could calculate the depth with amazing accuracy. Their estimate, 10,983 meters, plus or minus just 6 meters. They used the sound of destruction to map the void. But what about the sounds that originate in the trench? Is it just a silent, crushing desert? Not at all. This is where the story gets truly magical. For years, if you had asked a scientist what the deepest, most pressurized place on Earth sounded like, they might have guessed it was a place of near silence, broken only by the occasional groan of the Earth. But then they heard something weird, something that didn't fit any of the rules. It was a sound so strange, so otherworldly, that it stumped the experts for an entire decade. This story begins back in 2014. Scientists were conducting an acoustic survey of the vast area around the Mariana Trench using autonomous underwater gliders, kind of like robotic, listening drones. In the midst of the expected low rumbles, their equipment picked up something bizarre. The sound was so unique that the researchers who first heard it had to come up with a new name for it. They called it the biotwang. So what does a biotwang actually sound like? Imagine you're listening to a deep, sonorous groan, the kind of low moan you might associate with a very large, tired animal. But then, right in the middle of that moan, the sound twists. It suddenly leaps into a high-pitched, metallic, squeaky echo. Some of the researchers described it as sounding like a frog burping in space. Others had a more pop culture reference. They said the high-pitched part reminded them of the sound effects used for the Starship Enterprise in the original Star Trek series, that distinctive bip-boo noise. Another comparison was to the mechanical roars of the Leviathan in the animated film Atlantis, The Lost Empire. It was, in short, not a sound anyone would naturally attribute to a living thing on our planet. As Ann Allen, a research oceanographer with the National Oceanic and Atmospheric Administration, NOAA, put it, your average person would not think that it was made by an animal. They would think it was some ship or the Navy. Naturally, the mystery captured imaginations. The sound had all the hallmarks of a great deep-sea enigma. Was it some undiscovered giant creature? A strange geological process? The initial clues pointed away from the truly fantastical and toward the gigantic animals we already knew lived in the ocean. The structure of the sound suggested it was a biological call, and its power and low-frequency components hinted it was probably from a baleen whale. Baleen whales, like blue whales and humpbacks, are famous for their complex, powerful songs that can travel across entire ocean basins. Scientists even joked that there are enough other Star Wars sounding whale calls that they guessed it was made by a baleen whale. But there was a big problem. This biotwang didn't match any known whale call in the scientific catalog. It was a complete acoustic outlier. Solving a mystery like this in the open ocean is incredibly hard. You can't just peek over the side of a boat. To definitively prove what animal makes a sound, you need the perfect alignment of time and place. A person on a research vessel has to visually spot and identify an animal at the exact same moment that the mysterious sound is being recorded by your hydrophones. As Ann Allen described, it takes a lot of time, a lot of effort, and a fair amount of luck. For years, that luck didn't strike. The Biot Wang remained a fascinating question mark in the deep-sea soundscape. The breakthrough finally came during a dedicated month-long survey for marine mammals near the Mariana Islands in 2018. The research teams were out on the water, eyes scanning the surface, ears listening to the live feeds from underwater microphones. And then they got lucky. On 10 separate occasions, they spotted a group of elusive whales known as Bride's whales, pronounced brudus. Bride's whales are baleen whales, but they are among the least understood of all the great whales. They are constantly on the move across tropical and temperate oceans worldwide, which makes them incredibly hard to study. Scientists don't even have enough data to reliably estimate their population numbers. Here's where the magic happened. On 9 of those 10 occasions when the researchers saw the Bride's whales, their hydrophones also picked up the distinctive sci-fi warble of the biotwang. Once could be dismissed as a crazy coincidence, twice might be happenstance, but 9 times, that's a pattern you can take to the bank. As Ann Allen succinctly stated, 9 times it's definitely a Bride's whale. The visual confirmation was the golden ticket, the direct evidence they had been searching for. The decade-old mystery was solved. The bizarre biotwang was the call of the Bride's whale. But solving the who only opened up new and even more interesting questions. Why did it sound so strange? And what were they using it for? The researchers have a leading theory. They suspect the biotwang might function as a contact call. In the vast, dark, three-dimensional space of the open ocean, keeping track of your family or pod members is a constant challenge. A unique, complex call like the biotwang could act like a sonic beacon. Imagine the whales playing a massive, slow-motion game of Marco Polo across hundreds of miles. One whale emits the call, Marco, and listens for the distant reply, Polo, from its companions. This would help them regroup after foraging dives or coordinate their movements across huge distances. Of course, as Allen cautions, we need more information before we can say for sure. The social lives of Bride's whales are still largely a secret. Now, with the source identified, the scientists wanted to learn more about these elusive whales. They turned to NOAA's vast archive of deep-sea recordings. Since 2005, NOAA has had passive acoustic recorders sitting on the seafloor in 13 remote locations across the North Pacific, silently collecting the ocean's soundtrack. This archive is unimaginably huge, over 200,000 hours of audio, amounting to more than 500 terabytes of data. Manually listening to all of that to pick out specific biotwang calls would be an impossible task. As Olaf Manek, a whale researcher from Griffith University in Australia, noted, it's so much data that it's simply impossible to analyze manually. This is where modern technology entered the story in a brilliant way. The research team partnered with Google. Google's AI for Social Good team provided artificial intelligence tools to tackle this audio mountain. Here, how it worked. First, the AI converted slices of audio into visual images called spectrograms. A spectrogram is like a musical score for sound. It shows how the pitch, frequency, and volume change over time. The biotwang, with its unique low-to-high jump, creates a very distinctive visual fingerprint on a spectrogram. The scientists then trained a machine learning algorithm, essentially teaching it by example, to recognize this fingerprint. Once trained, the AI could scour those 200,000 hours of recordings in a matter of hours, a task that would have taken humans years. What the AI revealed was a treasure map of Bride's whale activity. It showed that these specific biotwang calls are seasonal and come predominantly from the western North Pacific. This was another key piece of evidence. as it matched what little was known about bride's whale migration patterns. Interestingly, the data suggested that not all bride's whales around the world make this sound. It seems to be a distinct dialect of a specific population. Most fascinating of all, the AI analysis uncovered a clear link to climate. The data showed a big spike in biot wang detections in 2016. That year, a strong El Niño event, a climate pattern that warps ocean temperatures and currents, disrupted the ocean. It shifted the locations of the whale's prey, like krill and small fish. The AI-tracked sounds showed the whales followed their food, even showing up in places like the northwestern Hawaiian Islands, where they aren't usually found. This proved their movements are tightly tied to the shifting buffet table of the ocean, which is itself driven by large climate forces. This discovery is about so much more than just putting a name to a funny noise. It opens a powerful new window into the lives of these secretive giants. Before, tracking a constantly moving, rarely seen whale was nearly impossible. Now, scientists have a reliable acoustic tag. Every time they hear a biot wang on their hydrophones, they know a bride's whale is, or recently was, in the neighborhood. This passive acoustic monitoring is a game changer for conservation. As Lauren Harrell from Google's team said, once you know where and when the whales travel, AI models can connect those data to climate and environmental factors to support protection efforts. In a world where climate change is altering ocean ecosystems, understanding how whales like these adapt their travels to find food is critical to ensuring their survival. The story of the biot wang teaches us a profound lesson about the Mariana Trench and the deep ocean as a whole. It is not a silent desert. It is a living, breathing, communicating realm. The trench itself acts as a giant acoustic filter. As we discussed earlier, the extreme pressure and cold of the deep water absorb high-frequency sounds very quickly. But low-frequency sounds, like the deep moan that starts a biot wang or the rumble of an earthquake, can travel for incredible distances. This is why the ambient noise recorded at the bottom of the Challenger Deep is a constant, low-frequency symphony. When scientists from NOAA and Oregon State University first lowered a specially built titanium-encased hydrophone to the bottom of the Challenger Deep in 2015, they expected a world of hushed quiet. They were shocked by what they heard. You would think that the deepest part of the ocean would be one of the quietest places on Earth, said Robert D. Zayek, the project's chief scientist. Yet there is almost constant noise. Their recordings were filled with the booming thunder of near and far earthquakes, the distinct, mournful moans of baleen whales, sounds very much like the low part of the biot wang, and even the roaring chaos of a Category 4 typhoon churning the surface far, far above. They also clearly heard the hum of ship propellers from the busy shipping lanes near Guam, a reminder that human noise pollution now reaches every corner of the globe. This rich soundscape proves that life in the trench is deeply connected to the world above, not isolated from it. The whales that sing their biot wangs near the trench are listening to this global low-frequency network. They hear the earthquakes, the storms, and perhaps each other from hundreds of miles away. Their world is built on sound in a way ours is built on sight. The discovery of their call is a reminder that even in the most extreme environment on the planet, life finds a way, not just to survive, but to create, to communicate, and to weave itself into the very fabric of the Earth's processes. The mysterious biot wang is no longer a ghost in the machine. It's the voice of a giant, a signal in the deep, and a key to understanding how the creatures of the abyss navigate their immense, dark, and singing world. What's the point of all this? Why risk lives and spend millions to explore a place so hostile? It's because the Mariana Trench is more than a geological feature. It is a mirror. It shows us the extremes our planet is capable of. It shows us life's incredible will to adapt in ways that challenge our very definitions of what is possible. It shows us the profound quiet and the haunting songs that exist in our world, completely separate from our noisy human existence. And in its defiance of sound, it teaches us humility. It reminds us that for all our technology, we are still visitors in a realm that operates by ancient, immutable, and crushing rules. The silence of the trench isn't empty. It's full of the low hum of tectonic plates grinding, the distant songs of whales filtered through miles of ocean, the clicks of deep-sea creatures we've yet to discover, and the quiet, resilient pulse of life itself under the ultimate pressure. It is the sound of Earth's deepest breath. And with that, we surface from the deep. If this journey into the silent, screaming depths of the Mariana Trench captivated your imagination, do me a huge favor. Give this video a thumbs up. It really helps others find these stories. And if you haven't already, subscribe to the channel. We're just getting started exploring the wonders and mysteries of our world. I am genuinely curious to know who's out there watching. So let me know in the comments, where are you tuning in from and what time is it for you right now? Are you watching with your morning coffee, on a lunch break, or late at night? I read every single one. From the deepest part of the ocean to wherever you are on this beautiful, fragile planet. Thank you for watching, for wondering, and for exploring with me. Take care of yourselves and each other. Good night.